This we're going to talk about roller coasters that aren't 100% efficient. So with 100% efficient roller coasters, we just say energy is going to be the same the whole way along. 100% efficiency works like this. This is the easy story, okay? Oh, by the way, if there's anything that makes me want to go to South Korea, it's this roller coaster right here. It's 56 meters tall. Look at it if you want to. And just to give a context for 56 meters, if you're a foot person, that's 150-ish feet, 160 feet. That's a lot. And if you're somebody who doesn't understand what that is, that's like, I don't know, look up the Niagara Falls if you like, but I think that's about 80 meters or something like that. This is like twice Niagara Falls as a roller coaster. This is a kick butt roller coaster. And if anything's going to pull me to South Korea, it's going to be this thing. I mean, obviously, the delicious food also, and the Korean people, but still, roller coasters. All right, so the height of the first hill on this roller coaster that we're just going to deal with is only 10 meters. So not as fancy as the roller coaster that I just described. And then we're going to get to a height B a little later on, and then we get all the way down to height C. It's like Baby Bear, okay? And for a 100% efficient roller coaster, we just say E total A is equal to, and we could just choose B or C. I'm just going to pick on C. Like, how fast can this thing go? E total at position C. And we expand it out. EGA plus EKA equals EGC plus EKC. We expand out the energies, and we get mass times acceleration due to gravity times height A plus 1/2 mVA squared equals mass times acceleration due to gravity height C plus 1/2 mvc squared. And really the reason I chose position C was because some things zero out. Specifically what? Yes, sir? You got it. Gravitational potential energy where? At the beginning or the end?
It ends out at C.
At C.
You just cancel that one out, like fully.
Gone. All right. Now, based on our diagram, what else can I zero out? Yes, sir? Yeah, right here. Look, that VA is 0. So that one's going to be gone because anything times 0 is 0. And then we can jump over to, well, we can just write it out. Whatever's left over, AGHA is equal to 1/2 mvc squared. Yes?
Can we get rid of the mass there?
Ooh, yeah, your point. You're right. That's a good point. Since we didn't know the mass, we were told here that it was unknown mass. That's a great idea. We could divide both sides by m, thereby canceling out the m's. I love that. I love that for us. And we end up getting, oh, is it okay with you guys if I also multiply both sides by 2 while I'm at it?
Yeah.
All right, let's do that. 2 times AGHA equals, the reason I multiplied by 2 is to get rid of that 1/2 VC squared. And then I think I would just square root both sides to get VC all by itself, and I'll plug in my values. VC is equal to 2 times, we'll say we're on Earth, times height A of 10 meters, all rooted. And somebody with a calculator help me out. It rhymes with splort mean. What is it? 14. You're right. That's good. 14 point what? Reminds me of a famous spy. What's that?
0.007.
Yeah, 007. That's right. Meters per second. And then if we're going to round it off to how many sig figs does it look like? 3? 14.0 meters per second. Now that's for a 100% efficient roller coaster. And so just like as a warm-up, that's what we're going to do. I want to take it down to something even simpler. A slide. Now this is a fancy slide because it's a 10-meter tall slide, like 30 feet up in the air if you're a foot person. And so it's like a carnival slide. Okay, but like a nice big slide. So I got this kid that's sitting at the top of the slide. And part A says, find the child's EG at the top of the slide. Well, no problem. We've got a 10 kilogram kid, so mass is equal to 10.0 kilograms. That means that EG is going to be equal to mass times acceleration due to gravity times height. And you know what? This kid's going to go down a slide, so why don't I just like say this is position 1, and when they get down to the bottom, that'll be position 2. That'll just help me to keep myself organized. EG1 involving H1. 10 kilograms. I chose nice round numbers, so I know that there's people that have already done this in their heads. Just give me a second to write it down before I take your answer. 10 meters up in the air. Who's got it? How many joules? What is it? 981. Nice. 981 joules. And we don't even have to round on that one. Rather than taking time on therefore statements, I'm going to just keep on going. It says, find the child's kinetic energy at the bottom if the slide is frictionless. So this is our 100% efficient scenario, and we're going to throw a wrench into that in just a minute. But that means that if E total 1 equals E total 2, and EG1 plus EK1 equals EG2 plus EK2, well, isn't that just the same thing as what we did with our giant roller coaster before? We're just showing that just because it got smaller, well, it's not even smaller, it's the same height of slide. It just became simpler. It doesn't mean it's any different. I just say that guy 0 is out, that guy 0 is out, and so that means that EG1 equals EK1, and so we can say EK1 is equal to 981 joules for a 100% efficient slide. Now, I've never been on a 100% efficient slide. I imagine that it would be very, what do you think, rough or slippery? Sorry? Oh, EK2, thank you. Would a 100% efficient slide be very rough or slippery, though?
Slippery.
Slippery, yeah. Like, I mean, if you wanted to really make something a lot of fun, like a slide, don't do this, because people can get hurt. These slides are designed with a certain angle that assumes that they're not super slippery, right? Because if you poured oil on a slide, people could get hurt. Just saying. I've been on a slip and slide before, and it's different when the slip and slide has soap on it versus no soap. You ever experienced that? Like, and my brother-in-law one time got these giant tarps. We put these giant tarps in the backyard, and you know, like grown men trying to relive their childhood days. We got this giant tarp, and we just slathered it in soap all over the tarp and had the kids slide on it. Had a great time, right? Like it was enormous. It was like, honestly, it was the kind of tarp that you use to make a hockey rink. So we didn't even make it like a single run, like a slip and slide. We just made the whole area a giant slip and slide. Like the backyard was the slip and slide, and then ran the sprinkler over it and put soap everywhere. It was fantastic. I'm not saying that's like environmentally friendly or anything, but we did have a very good time, okay? So that would be reducing the friction. But I want to think about friction now. How much work is done by friction on the slide if Fk is 100 newtons? So we got to do a little bit of thinking here. I want to draw a free body diagram. If this is a person going down the slide, I know that they would have a displacement going down the slide. I know that working against them, notice I never attach displacements to free body diagrams. I would have a friction force going up the slide. And of course, friction steals energy from us. We've seen that with hockey pucks before. But the displacement is one way, and the force due to friction is the exact opposite way. So the angle between those two would be 180 degrees. That's the relative angle between the friction force and the displacement vector. If the Fk, I'm just writing my givens, is 100 newtons, and the displacement looks like the slant of my slide is 15.6 meters, then the work done on a kid going down this slide would be equal to Fk times displacement times cosine of theta. We sub in our values, 100 newtons. Remember, I don't have to care about reference frames because the angle takes care of it. Times 15.6 meters times cos of 180. What's special about cos of 180? It's equal to, yeah, -1. Great. So I don't even have to type that in. I've got it. And I've left some numbers nice and round here. So what's 100 times 15.6? Yeah.
Negative 15,600.
Close.
Sorry, 1,500.
Yeah, negative 1,560 joules. All right, so I look at this and I say, okay, if this kid goes from top to bottom, friction's going to steal 1,560 joules from the kid. Here's the problem, though. Does the kid have that many joules to give away? Look, if this was money, they only got 981 joules in the bank. Friction, if you're going to complete the slide, wants to steal more than you've got. Effectively, what does this mean the kid's going to do?
Push himself forward.
Yeah? Well, he'll move. Is he going to get to the bottom, though? No, it looks like somehow he's going to only make it partway down before he runs out of energy. All right, well, let's change it. Let's just say how much work is done by friction on a child if we grease up the slide. Now, don't do this. don't modify a slide, okay? Every once in a while, there's some idiot that goes and damages city property. Don't be that idiot, okay? But if we did, on our own private property, work is equal to force times displacement times cosine of theta. Now the cosine of theta is still going to reduce to -1, because it's still the same free body diagram. But if we were to lube up this slide or polish it or whatever it is that we would do to make slides more slippery, and it became half as frictional, then you get negative 780 joules for a full slide down. Do we have enough energy in the bank now?
Yeah.
Okay. So then, based on D, how much kinetic energy does the kid have at the bottom? All right, well, that's not a problem. E total, 1, plus the amount of work due to kinetic friction, if we want to call it work K, which seems weird, equals the total energy at position 2. We could talk about it that way. And we've already calculated the work done by kinetic friction. So 981 joules plus the negative 780 joules equals E total at position 2. E total at position 2, we can probably do this math in our heads. What's 981 minus 780? 201. 201 joules.
What did you do last that one?
So the total amount of energy that I have at the beginning minus how much energy I steal from my system is how much energy I have in my system at the end.
Then above we say E2 is not going to be 1. That's for 100%.
Yeah,
So this one's for not efficient?
this is for an inefficient system. Yeah. The total amount of energy I have just by being there plus how much work somebody does to it is how much energy I'm going to have in the end. So I got 201 joules. And then, of course, I think it stands to reason if we wanted to do this, I'm just going to call this part E primed. A little extension on E. How fast is the kid at the bottom? Because we'd like to make sure that the kid gets there. I think we've all been on slides. If we're being honest, we've enjoyed slides in our time, right? But you get to the bottom of that slide. You know that slide where you get to the bottom and all of the energy has been robbed of you from friction, and you just like barely get to the bottom, and then you get off, and then you climb up again because you're a kid and you don't know any better. But like as an adult, wouldn't you like to be like still going like at a high speed when you hit to the bottom? You know, like as a teenager or whatever. I want to know how fast we're going. As a slide designer, that speed at the bottom should be almost 0 because we don't want kids to be slipping off the end and falling on their bums or cracking their heads. As a kid, wouldn't you want to be going fast because you don't care about safety because you're a kid? You know how it is? So let's say EK is equal to 1/2 mv squared. That's how much energy we have at the bottom. E total is how much energy we have at the bottom. So V is equal to 2 times EK over m, all rooted. So 2 times that 201 joules divided by, what was the mass of this kid? I think we knew, 10 kilograms. That's a small kid, I think. This kid should not be left unattended. How fast is the kid going when they get off the bottom? Yep.
6.34.
Oh my gosh. I feel like this is not a safe slide. 6.34 meters per second. That's pretty fast. I mean, you multiply that by 3.6. What's that by 3 times 3.6 to get in kilometers per hour?
22.83.
Oh my gosh. If you had your baby, this is a 10 kilogram person. If you had your baby shooting off the end of the slide at 22 kilometers an hour, you'd probably be calling the city workers, right? Like there's a safety issue with this slide. So we might want to fine tune this. Can you imagine that people might want to fine tune this friction value so that we bring the kids back down to a reasonable final speed, right? And it's crazy. You never think about the invisible world of safety, but that kind of thing actually gets thought about when we make slides so that we don't have kids slipping off the end at like 20, 30 kilometers an hour. That's something that people really do think about. And it might be by trial and error, or it might be by calculations like this. Now, another thing we can talk about is percent efficiency. Percent efficiency is a measure of the final energy of the system divided by the initial times 100%. And it's kind of like getting a score on a test, you know? So if I had the final energy, like in this case, 201 joules, and the initial energy at the top of the slide was 981 joules, then we could have an efficiency rating for our slide. And if I kind of like a score out of the possible total, right? And if I did this calculation, did you get it already? What did you get?
20.5.
Nice. I think that's rounded off to 3 sig figs already, right?
Oh, yeah. It was 24.489.
Okay, 20.489. Yeah. I didn't really need the unrounded one, but I mean, like, let's acknowledge rounding. So 20.5% efficiency. And so we typically express efficiency as a percentage, kind of like you would express a mark on a test as a percentage. It's a mark out of the total that could happen, right? 100% would be 981 joules still in the system, as opposed to being lost to friction or thermal heating or something like that.